In the previous video, we met the class P, which consisted of decision problems that could be solved in polynomial time. Now we introduce another important class of problems known as the NP class. To motivate the discussion, consider the problem of finding a cycle in this graph, which goes through every edge exactly once. It turns out that there is a nice property that guarantees that such a cycle exists if and only if all vertices of this graph have even degree. Since many vertices of this graph are of degree 3, we know that such a cycle does not exist for this graph. However, in general, we can check whether this is true for any graph by iterating over the set of vertices. This will take time linear in the number of vertices, and hence the problem is in P. Now let's consider a similar problem, but this time, instead of edges, the restriction is on vertices. You have to find a cycle that goes through every vertex exactly once. It turns out that this time there is no nice property that guarantees an efficient solution. No one has found it yet. Seems like the best we can do is to iterate over all cycles in this graph and check if any of them fulfills the criterion. Only problem is, there could be n factorial such cycles, and n factorial is not a polynomial. It is what we refer to as exponential in n. It is remarkable that two apparently analogous problems are different in their hardness. We haven't been able to solve one of them efficiently. The first one is called the Euler cycle problem, and the second one is called the Hamiltonian cycle problem. So we can now ask, does the Hamiltonian cycle problem belong to a possibly larger class of problems? Notice something peculiar about this problem. If I give you a cycle that I claim is Hamiltonian, you can verify my claim efficiently. What you would do is simply iterate over every edge in the cycle and check whether the cycle goes through each vertex once. This verification would require linear time in the size of the overall input, and that's what the NP class consists of. The Hamiltonian cycle is in the NP class because its solution can be verified in polynomial time. We call the proof that is presented to the verifier the certificate. In the case of the Hamiltonian cycle, the certificate looks like the cycle of a graph. You can think of the verifier as a function v that has a problem instance x and a certificate c, and outputs yes or no based on whether the certificate is a valid proof of the instance x. In the case of the Hamiltonian cycle, the problem instance is a graph and the certificate is a cycle graph. The verifier would check the graph against the cycle and output yes only if it is a Hamiltonian cycle. So the class NP is defined to be the class of languages that have polynomial time verifiers. Here the verifier is supposed to be polynomial time with respect to the size of the problem instance. So how do we decide that a problem is in NP? Well, we simply give a valid certificate and a polynomial time verification algorithm. Let's look at a few examples in the NP class. The SAT problem is a canonical example. It consists of the set of satisfiable Boolean formulae. A Boolean formula is satisfiable if there exists an assignment of truth values to all variables comprising the formula. How would you decide that it is in NP? Remember that you need to give a valid certificate and a polynomial time verifier. A truth assignment for each variable is a valid certificate for this problem. You can think of it as a list of true or false values where each index corresponds to a variable. This list can be used to deduce the truth value of the Boolean formula. You can imagine that every literal in the Boolean formula is substituted with its corresponding truth value, and then the overall truth value of the formula is deduced by repeated substitutions. This procedure will take time linear in the size of the formula, which is of course polynomial time. Hence the SAT problem is in NP. Now let's look at a graph problem called Clique. A clique is a fully connected subgraph of G. That is to say, if you choose any two vertices from the subgraph, there will be an edge between them. Coming up with a polynomial time algorithm for checking whether a size k clique exists in a graph has proved futile so far, but it can be efficiently verified given a certificate. Can you think of one? Well, a fully connected k-vertex subgraph of G is a valid certificate for this problem. The subgraph can then be efficiently verified for number 1 being fully connected, and number 2 checking it against the original graph to see if it is a valid subgraph. Checking 1 will take time proportional to the number of edges, which is quadratic in the worst case, and checking 2 will also take time quadratic in the worst case, which is polynomial time overall. Hence the clique problem is in NP. Finally, let's look at the Euler cycle problem from the beginning of the video. We know that this problem is in P. But is it also in NP? Why, yes it is. If you can solve a problem in polynomial time, you can certainly verify it in polynomial time as well. The verifier can simply ignore the certificate and work with the problem instance alone, producing the answer in polynomial time. And this leads us to the realization that all problems in P are in NP. So we can now ask, is P a proper subset of NP? In other words, is there any problem in NP that is not in P? Turns out that in spite of 5 decades of work on this question, we are still not sure about the answer. Is P a proper subset of NP, or is it equal to NP? A lot depends on this answer, as we will see in a later video. Meanwhile, let's return to the NP class and define it again, this time using the notion of the n-time class. The n-time class is the non-deterministic Turing machine analog of the time class, otherwise defined exactly like time. And just like the P class was the union of all polynomial time classes, the NP class is the union of all polynomial n-time classes. This helps us see what the n in NP really stands for. It stands for non-deterministic computation. Both this definition and the definition that involves verifier and certificate are formally equivalent. They are simply two ways of saying the same thing.